Okay, QT, whoops. Let's look at the next one. This is another example, just to give you an idea. I call it, well, the name should give you a hint on what's happening. What's going on?
Swapping stuff.
Yes, but what's going to happen?
Reswapping where they're saved.
Okay, so what's, a little more specifically, what's happening?
You're starting with the data address.
Oh, is this one going to run right?
Okay, you don't have a label for your okay, those are your data, never mind.
Yeah, you don't have to technically. You could try and encode it yourself.
Sure.
It's a terrible idea, but I'm showing you can't do it. Yeah, it is gross.
It smells.
What's it doing?
So you're taking the two words there. You're gonna load where it is from the start, and then you're gonna go one by one. Each load it into S1 and then S2, and then you're just gonna swap their places
In memory.
in the memory.
Yeah. All right. This is the make sure everyone's following and paying attention. Hey, look, our
Where did you
data.
get the data start address from?
What's that?
Where did you get the data start address from?
We just manually encoded it. See, it popped up. I can go over to data, and you know we can go fast. Just run it. Hey, look, it flopped. It swapped. All right. We good?
Yeah.
Whoa.
Whoa. All right. Function calls. All right. Now we should go do some slides here. Please tell me we have function calls. We don't have function calls. Do we really not have function calls? These slides are terrible.
Lies, lies,
What?
lies, lies, lies.
Oh, yeah.
Ah, Underwood.
Are these his slides?
Yep.
Oh.
All right, procedural call, stack frame. We must now understand what the stack frame is. If you recall, when I did data structures, I painstakingly showed you every time you call a function call, you allocate memory on the stack, you create your local variables, and every time you call another function, you got to create it on the stack, so forth and so on. Now you must manually do that in assembly.
Gross.
There, okay.
That was convincing.
Oh, man, all right.
I like that
So
know
you can
how-
pass values into the procedure using those addresses that MIPS has, and we went over those registers that MIPS had last class. But you know, let's jump back and look at them again,
Okay.
right? Because you didn't memorize them, did you?
No.
So there's 32 registers, 0 through 31. Our register 0 is always 0 by convention. AT is reserved for the assembler. In other words, don't use it. V0 and V1 are how you return from a function. Remember, your function could return an integer or maybe a double or something. You would use those two registers for that. A0 through A3 are the parameters to a function. So what does that imply, the number of parameters you can send? 4. If you had more than 4, what would you have to do?
Sadness. You have to store it in memory.
Yeah, there you go. Store it in memory.
Gross.
All right, you have 10 temporary variables. You have a saved variable. I completely forgot what that did. And you have more temporaries. Actually, this goes to T7 and that goes from T8 to T9. Yeah, I forgot what the save does.
Does it just save it at the different spot?
Yeah, cross function call. I forgot what it saved it for.
No, apparently we don't use it enough.
No, we don't.
So that those temporary variables, those 10 temporary, those are the ones that we would update to do addition with and stuff like
Yeah,
that?
you use those to do all your work.
Okay, so we wouldn't be using like 9 and 10, we'd be using like 6 and 7.
Right. 9. Well, hold on. 9 and 10. Temporary 0 through 9 you're allowed to use at any time for
And
anything.
that, I was saying that because in that MIPS thing we were doing, we updated registers 9 and 10 to do addition.
Yeah, and register 9 is a temporary, right? Right. So, yeah, that's fine. Global pointer, frame pointer, stack pointer, you just need to be able to carefully manipulate these. The way you edit the stack pointer is how you do function calls with the assembly. And the return address is how you store where you're coming back from.
Yeah.
All right, now let's fast forward. Okay.
Whoa, that was a lot of fast forwarding.
Yep. First off, you need to allocate your memory on the stack of what your function's going to do. You use your frame pointer to top, that points to the top of the stack, so in general, don't touch it. And the SP pointer points at the bottom of it, and that's the one you are going to manipulate for your function calls.
Don't touch FP.
And yeah, don't touch FP, you're going to manipulate the stack pointer. Why not use global memory? Well, we could, but what if your function is calling another function? You need to be able to store your return trace all the way down many functions. For example, if you were to do recursion in your lab, you need to actually, and you don't know how many function calls you're actually doing, you can't just globally memorize the return address, and that's why you need a stack. Make a little more sense when we get to it. What does a stack frame need? It needs to allow the callee access to registers without a constant push pack, right, because that'd be too expensive. You need to be able to return to the stack. Okay, you know, this is getting kind of dumb. Let's go to the code. All right, I make an array. 5, 4, 3, 2, 1. Beautiful. Any questions?
Why those numbers?
Why not?
Gross.
Those numbers aren't gross.
You are gross.
Oh.
Totally gross.
Okay, so this one, wow, this does nothing. This is just to show you what a function call does. Oh, it's going to swap. Okay. This, I don't think this does anything.
Sideways?
Yeah, this doesn't make any sense. Load address into array. Add load 0 for the second argument. Okay, AKK.
Did you make this?
I don't think so.
Oh.
Set up a return address. Actually call the swap function, which is, oh, that's why it's not making sense. Here's swap. Huh, finally. Call the swap function. It's going to do a bunch of stuff. It's going to swap the contents of parts of the array and then return back. All right, this is the C code for swap.
Huh.
You pass it an array, K, you're going to swap the K value with K plus 1, and then you're done.
I'm glad that's in there.
Me too.
Sequence is understood.
All right, let's go load this up in qtspim real quick. qtspim. A lot of times it's easier if you look at the text. All right, we got 5, 4, 3, 2, 1, and 1's over there. And if you just run do it and see what happens, okay, it swapped the 4 and the 5. So that's what our final result is going to be. But we're going to do it via function call. So let me go ahead and reinitialize and load the file, which you have to do every single time. Let's go ahead and watch it one at a time. All right, we set up main. We're going to load A0, which is the beginning of the array, into register A0. A0 is reserved as an argument that you send to the function. Hence, if you recall in C, the first argument was the array. A here stands for argument, not array. We're going to load the value 0 for the second argument. So we're going to swap what's in index 0 with what's in index of 1. Now, don't look at 29, that doesn't make any sense. Add I, stack pointer minus 4. That means we are moving the stack pointer by 4. Subtracting is increasing the size because it grows from the bottom. If it's at the bottom and you want to move up to 0, you have to subtract. All right. Then we are storing the return address on the stack. Why are we storing the return address?
You know where to go back to when we're done.
Right. So when we return from this function, we need to know where we go from our current function, which is main. So if we go back to the stack pointer, where's the stack pointer? Oh my goodness. AC, so that's up here. If I hit one more time, there's the return right there. Got stored into memory. And now jump and link which is a hardware instruction to do function call supporting. We're not doing, by the way, if you go back to our assembler, or not assembler, our Verilog code, we're not implementing jump and link. That would be too complicated. So jump and link to swap. It's now going to call swap. We've set up the parameters for A0, argument 0, and argument 1, so we're ready to go. Let's see. I want you to watch what happens to the return address when we do jump and link. Notice that it changed. It changed to the instruction that's right after the jump and link. That's part of the jump and link instruction. Is it going to jump to the program counter, the first instruction of swap or your function, and then it's going to store the return address into RA for you. So it does both of those things in one instruction. Do we have any questions yet? Because we just made a function call by storing off our previous return address on the stack and then making the call.
So you have to store it first.
You have to store it first because once you do jump and link, it's going to overwrite RA all for you. I mean, by the way it works. Yes? Question?
Which was the one that stored it?
I was blessing DJ.
Okay.
That was the AW. Okay.
Blessing.
How are we doing? Okay. So we're going to take, what are we doing? Adding A1 and A1 together. That's a weird instruction. And then we're going to add those again into 9. Okay. A0 and T1. You know, I'm not even, that doesn't do anything up here. That's cute. A0 into T1, which will give us the memory address of the first element. We're going to load that value into register T0, which is 5, namely that guy right up there. We're now going to load the element afterwards. That's the 4 into T2. Then we're going to store, let's see, store what's in 10, which is T2, off in the beginning one. So if we go back to data, that 5 is going to become a 4. And then that 4 is going to become a 5 because we saved that in a different temporary in our register file.
Yeah. Just like C++.
Jump return address. So it's going to jump to the return address, which is what's value here. And what was that value?
The address we left off at.
The instruction after the jump and link when it was called. So when I execute this guy, we're back to the instruction right afterwards. Now we're going to restore our old return address because remember we stored that off in memory, namely right here, and that's the return address of main that was needs to be returned after main. So we're going to update the return address F10 so it's updated. We are restoring the stack pointer to its original size because we no longer need those 4 bytes. So this is freeing memory. Notice that you now have to manually do the memory allocation and deallocation of function calls because you're in assembly. The compiler would do that for you, but now since you're doing assembly, that is the memory error that you could have if you're leaking memory.
So always do that.
Yes. What the easiest way to do this, guys, is where is it? There's where you increase the stack. You made the function call. Really, these are the instructions. Increase the stack, store whatever you need in the stack, do the function call, load everything back out, decrease the stack pointer. Always do it in that order.
And basically, the same instruction to increase, but just go the opposite direction with the.
Yeah, and then you won't have problems. Do it in this order. Don't try and mix things up. Just do it in this order, and you will be able to pass your labs. What's that?
Just pass.
I can't say A because then that's, you know.
Then you have to give
That's
an
too
A.
hopeful,
Do it in
right?
this order,
Said
you'll
so.
pass.
Look, I've learned, from experience, I've learned you can't just say A because students will find something else to mess up, right?
Wow.
So we will
Yeah, you're
pass.
So right. So right.
So right.
Well, I
from
can't
so many
predict
ways.
all the errors you're going to make.
I'm not gonna make any this.
I will.
Confident.
Thank you, Jonah. All right, so we update the stack pointer. Notice the stack pointer is over here. It's going to be added. So yeah, back up to A0. Jump return address. This is us exiting main. Goes back up to that jump and link main, which we then do the syscall exit, and we're done.
Yay.
All right,
Yay.
everyone doing okay?
Yeah.
Kind of.
Kind of. All right.
We'll see once we get to our
I mean, I could use $1 million, but.
What comes next? Ooh, system calls.
$1 million comes next.
This does not have the system calls, does it? Wow, there's a lot of
Great.
convention here.
I think
Okay,
you
good.
actually have to remake the thing.
Yeah, I will have to. Note to self: remake the assembly slides. Okay. A couple of conventions occurs from the call the allocate memory for the frame, and we're talking about the stack pointer grows downward. That's why we subtracted it first. Save any saved registers. That's what S is saved registers between function calls. Caller expects these values to be preserved across all calls, so if you need to use these, you need to save them and write them back out. The attempts you can go and overwrite all you want. Return address is only needs saved if callee will call another function, which you should always assume is going to happen. We don't care about the frame pointer.
Because we don't use it.
Return values come from V0, V1 if needed. Make sure you restore them and then jump to the return address. Namely, if you're doing a function call and you're using any registers that are not the T registers or the A registers, you need to save them and then load them back out because those need to be preserved. All the other ones you can mess with all you want.
All the ones that are labeled T, we can mess with.
T you can mess with and A you can mess with.
Okay.
But the rest, no.
And AT.
And what?
AT.
AT. Wait. AT.
T.
No.
AT.
That's a reserve one you can't touch.
Yeah, don't touch that.
Don't touch.
That was the joke.
Okay. So just reserve. Yeah.
Yeah. Solid.
Thank you, Kalia.
So, that's.
Thank you, David. Thank you, David. All right.
PJ would have laughed if he was here. You know? Nothing.
Just making jokes.
Wow, I cannot type today. You want to learn more about the stack pointer?
Sure.
Whatever you say.
All right, just to
Do we
drive this
actually have a
home.
real choice,
No.
so just go for it.
All right, MIPS memory is reserved as a stack. It does not have push and pop instructions like x86, so you have to do it manually, which is what we just did. You push elements by increasing the stack pointer.
What is going
Or
on there?
wow, this is backwards.
Why is it on
Drawings.
Drawings.
Yeah, who did this?
And Underwood's really bad handwriting.
I don't think this was Underwood.
Then what'd you do?
It looks too nice to handwriting to be.
We're not doing this. Forget these slides.